Starship is the largest and most powerful rocket ever built, a stainless steel giant taller than a 30-story building, capable of producing more thrust than any machine humans have ever flown. It has climbed to space. It has been caught out of the sky by the arms of its own launch tower in one of the most astonishing feats of engineering ever attempted. It has even begun deploying satellites, carrying real payloads to orbit. By almost any measure, it is a triumph, the vehicle that is supposed to carry humans back to the moon and, eventually, to Mars. And yet, standing between this magnificent machine and the operational missions it was actually built for, the crewed lunar landings, the voyages to Mars, the whole reason it exists, there is a single problem. One problem. Not a lack of power, not a lack of ambition, not a lack of money or engineering brilliance. One specific, stubborn, unglamorous technical challenge that no amount of raw thrust can muscle through. That has never been done at the scale required, and on which every one of Starship's grandest missions completely depends. That problem has a deceptively simple name: refueling, or more precisely, the transfer of ultra-cold rocket propellant from one spacecraft to another, in orbit, in the weightlessness of space. It sounds almost mundane, the kind of thing you would assume was solved long ago, a routine top-up at a gas station in the sky. It is not solved. It has never been done at anything close to the scale Starship needs, and it turns out to be one of the hardest problems in all of spaceflight. A knot of physics and engineering that has to be untied before Starship can do the very things it was designed for. You can build the most powerful rocket in history, and land it, and reuse it, and deploy satellites with it, and still be completely unable to send it to the moon with astronauts aboard, because of this one thing. And so this is a story about that single problem, about why it exists, why it is so hard, why everything hinges on it, and why the future of humanity's return to deep space may come down not to fire and thunder, but to the quiet. Fiendishly difficult act of moving cold liquid from one tank to another, a quarter of the way to nowhere, in the dark and the vacuum of orbit. Picture the scene that has to work, the moment everything is building toward. 200 miles above the Earth, a Starship coasts in orbit, its great tanks nearly drained from the climb up. Waiting, it is one of the largest objects ever placed in space. A silver tower gliding silently over the curve of the planet, and rising to meet it comes another, a tanker, freshly launched, its own tanks heavy, with hundreds of tons of super cold propellant. The two ships must find each other in the vastness, close the distance at a careful crawl despite both hurtling around the planet at 17,000 miles an hour, and come together, joining tail to tail so that the plumbing of one connects to the plumbing of the other. Then, with the two giants mated in the dark, small thrusters fire to nudge the joined stack ever so gently, coaxing the weightless, boiling liquid inside to settle toward the outlets, and the transfer begins. Hundreds of tons of cryogenic methane and oxygen flowing from the full ship into the empty one. Across the sealed connection, without leaking, without freezing, without exploding, until the receiving ship is filled and ready to go on. That is the act. That is the single thing that has to work, over and over, that everything else is waiting for. It sounds, described plainly, almost gentle. It is one of the most difficult things anyone has ever tried to do in space. And until the day it works cleanly and completely, the mightiest rocket ever built cannot leave the neighborhood of the Earth. Let me start by explaining exactly what the problem is, because to understand why it matters, you have to understand precisely what has to happen. The plan for Starship's most important missions, above all the mission to land astronauts back on the surface of the moon, does not involve a single rocket launching and flying all the way there on one tank of fuel. It cannot. Instead, it requires a Starship to launch into orbit around the Earth and then to be refilled with propellant while it is up there, before it continues on to its destination. And refilling it is not a matter of one quick top-up. It requires a whole series of separate launches of other Starships, tanker versions, each carrying a load of propellant up to orbit, where they transfer that propellant, tank to tank, into a waiting ship, over and over, launch after launch, until the ship destined for the moon is finally full enough to make the journey. So the single problem, stated plainly, is this: Starship must be able to transfer enormous quantities of extremely cold liquid propellant between two spacecraft, in orbit, in weightlessness, reliably, repeatedly, and quickly. And this has never been done. Not at this scale, not with these propellants, not by anyone. It is the one capability that the entire architecture of Starship's deep space missions is built upon, and it is the one capability that has not yet been proven. Everything else, the launching, the landing, the catching, the reusing, is either done or clearly within reach. This one thing is the wall. To understand why Starship even needs to be refueled in orbit, when older rockets flew to the moon without any such thing, you have to understand a merciless piece of physics called the rocket equation and the trade that Starship made. Getting to space is astonishingly hard because a rocket has to carry not only its payload, but also all the propellant it will burn, and that propellant is heavy, and carrying it requires burning more propellant. In a punishing spiral that means the vast majority of a rocket's mass at liftoff is fuel. To go somewhere far, like the moon or Mars, you need even more propellant, which makes the problem dramatically worse. The old moon rockets solved this by being enormous and almost entirely disposable, throwing away giant stages along the way, so that only a tiny capsule actually completed the journey. Everything else discarded to shed weight. Starship makes a completely different bet. It is designed to be fully and rapidly reusable, the entire vehicle flown back and used again, which is the key to making spaceflight dramatically cheaper. But reusability comes at a cost, because to fly itself back and land, the ship has to keep its engines, its structure, its heat shield, and reserve propellant, all of which is weight it carries the whole way. The result is that when a reusable Starship reaches orbit, it has used up almost all of its propellant just getting there, and has very little left to go any further. It arrives in orbit powerful, enormous, reusable, and nearly empty. It has the capability to go to the moon or Mars in principle, but not the fuel, because it spent its fuel becoming reusable. And the only way to give it the fuel to continue without abandoning reusability and without building an even more impossibly gigantic rocket is to fill it back up once it is already in orbit. Refueling is not an optional extra bolted onto the plan. It is the direct, unavoidable consequence of the fundamental choice to make Starship fully reusable. The price that choice demands, and there is no version of the reusable deep space mission that does not require it. And you might ask, why not simply build a bigger rocket or launch it full and skip the whole orbital refueling problem? The answer is that the physics does not allow it, and this is worth sitting with, because it explains why there is no shortcut. If you wanted a single reusable Starship to launch from Earth and fly all the way to the moon's surface and back without refueling, the rocket equation says it would have to be so gigantic, carrying so much propellant, that it becomes utterly impractical, beyond anything that could be built or launched. The amount of extra fuel needed to carry the fuel spirals out of control. This is exactly why the reusable architecture forces the refueling approach, because launching a mostly empty ship to orbit and filling it there is dramatically more efficient than trying to launch a full one all in one go. You break the impossible single launch into many achievable ones. But that efficiency comes with the requirement that you must be able to transfer the propellant in orbit, which trades one impossible problem, an absurdly gigantic single rocket, for one merely very hard problem, orbital refueling. SpaceX chose the very hard problem on purpose because it is the only path to the goal that the physics actually permits. There is no design cleverness that eliminates the need, no bigger tank or better engine that makes it go away. As long as the vehicle is fully reusable and the destination is deep space, the propellant has to be delivered in orbit, and so the entire edifice rests, by mathematical necessity, on cracking the refueling problem. It was never a problem SpaceX could design around. It was a problem they had to walk straight into. Now here is where the difficulty starts to reveal its true depth, because it is not one refueling. It is many, and that turns a hard problem into a daunting one. A single Starship headed for the moon does not need a splash of propellant. It needs to be nearly completely refilled, its huge tanks topped back up after being drained getting to orbit. And a tanker Starship can only carry so much up at a time. So filling one moon-bound ship requires not one tanker flight, but a whole series of them, launch after launch, each delivering a portion of the total, with the propellant accumulated in orbit until there is finally enough. Estimates of exactly how many tanker launches are needed vary, but they are not small numbers, ranging from several to well over a dozen, depending on the assumptions, an entire campaign of launches to fuel a single mission. And that requirement cascades into another one, which is flight rate. To launch that many tankers to fill one ship, and to do it before the propellant already delivered has time to be lost, you need to be able to launch Starships not once in a while, but frequently. Rapidly, one after another, turning the vehicles around and flying them again on a cadence no rocket in history has ever come close to achieving. So the refueling problem is not just about the physics of moving liquid between two tanks. It is about doing it as the culmination of a punishing operational tempo, a fleet of reusable ships launching in quick succession, each one performing this delicate transfer, all racing against time. The single problem, on closer inspection, is really a demand for an entire capability that does not yet exist, a rhythm of launch and transfer and launch again that would represent a complete transformation in how often and how reliably rockets can fly. And it helps to make the sheer quantity concrete, because the scale of what has to be moved is part of what makes this so daunting. A Starship's tanks, when full, hold well over 1,000 tons of propellant, a mass comparable to a fully loaded jumbo jet, several of them, in supercold liquid. To refuel a ship in orbit is to transfer something on that order, gathered from many tanker loads, high up in space, in weightlessness. This is not the delicate transfer of a few gallons to top off a satellite. It is the movement of an enormous mass of liquid, more than most industrial operations handle on the ground, conducted in orbit, between vehicles, against the constant loss of boil-off. Every ton of it has to be launched from Earth in the first place, which is why so many tanker flights are needed, and every ton has to make it into the receiving ship before it warms and escapes. When you picture the problem, do not picture a hose and a nozzle. Picture the contents of a small lake of the coldest liquid imaginable, having to be lifted into orbit in pieces and reassembled there, quickly, without spilling a drop into the vacuum, into a single waiting ship. The mundane word refueling hides the staggering, physical scale of the thing, and the scale is a large part of why it is so hard, because everything that is difficult about handling cryogenic liquid in space becomes far more difficult when there is simply so much of it to handle, and to make all those launches add up to a single fueled ship. The plan calls for an even more elaborate piece of choreography, a dedicated propellant depot in orbit, and understanding it shows just how much has to work together. Rather than have a dozen tankers each try to find and refuel the actual moon-bound ship one at a time, the architecture calls for a special depot version of Starship, a kind of orbiting fuel tank, launched and left in orbit to serve as a gathering point. The tankers launch, one after another, and each one rendezvous with the depot and offloads its propellant into it, so the depot slowly fills up over the course of the whole campaign. Then, when the depot is full and the moment is right, the actual mission ship, the one carrying the crew or the cargo bound for the moon, launches, meets the depot, and takes on its full load in a single transfer, topped off and ready to depart. It is an elegant solution to the problem of coordinating so many launches, but look at what it demands. It means the depot itself must store huge quantities of cryogenic propellant in orbit for an extended period, fighting boil-off the entire time, which requires advanced insulation and thermal management to keep the fuel cold for as long as the campaign takes. It means not one kind of orbital transfer, but a whole system of them, tanker to depot, again and again, and then depot to ship. It means multiple rendezvous and dockings, multiple connections and disconnections, all of them having to work flawlessly. The depot turns the refueling problem from a single hard transfer into an entire orbital fuel logistics operation, a supply chain in space, and every link in that chain is a version of the same unsolved problem, performed over and over, with the whole mission depending on none of them failing. And now we come to the heart of why the transfer itself is so brutally hard. And it starts with the nature of the propellant, because Starship runs on liquids that do not want to be still, or warm, or anywhere at all. Starship burns liquid methane and liquid oxygen, and the word liquid is doing enormous work there, because these substances are only liquid at staggeringly low temperatures, hundreds of degrees below freezing, cryogenic cold. Kept that cold, they are dense liquids you can pump. But everything in the universe that is warmer than they are, which is essentially everything, is constantly trying to heat them up, and the moment they warm even slightly, they begin to boil, turning from liquid into gas. In space, sunlight beats down on the tanks, with nothing to block it. The vehicle's own structure conducts and heat, and the propellant is perpetually, relentlessly warming and boiling away, a process called boil-off. Every hour that the cryogenic propellant sits in a tank in orbit, some of it is lost to boil-off, evaporating into gas that has to be vented or managed. This means the entire refueling campaign is a race against the clock. The propellant delivered by the first tanker is already boiling away while you wait for the second, and the third, and the 10th. Take too long to assemble the full load, and you lose it faster than you can deliver it, and the mission becomes impossible. So the whole operation must be conducted quickly, and the propellant must be kept as cold as possible the whole time, insulated, shaded, actively managed, in an environment that is doing everything it can to warm it up. Managing these boiling, fleeing, ultra-cold liquids in the harsh thermal environment of space for long enough to gather and transfer the enormous quantities required is a problem that has defeated or been avoided by essentially every space program before, and Starship cannot avoid it, because these are the propellants it runs on, and orbit is where it must be filled. And then there is the problem that sounds almost like a riddle, the strange and counterintuitive behavior of liquids and weightlessness, which turns the simple act of pumping fuel into something genuinely bizarre. On Earth, moving liquid from one tank to another is trivial, because gravity does most of the work. The liquid sits obediently at the bottom of the tank, and you put your pump or your outlet at the bottom, and gravity keeps the liquid there, pressed down, ready to flow. In orbit and weightlessness, there is no bottom, there is no down. The liquid does not settle anywhere. It floats, forming blobs and films, clinging to the walls, drifting in the middle of the tank in great wobbling masses, going wherever the last motion of the vehicle sent it, with no gravity to gather it into a pool you can draw from. This makes the seemingly simple act of getting the propellant to flow out of one tank and into another shockingly difficult. You cannot just open a valve and pump, because the outlet might be surrounded by gas instead of liquid, or the liquid might be scattered in droplets throughout the tank. You have to somehow gather the floating propellant and hold it against the outlet, and the usual trick is to gently accelerate the whole spacecraft, firing small thrusters to create a tiny artificial gravity that settles the liquid toward one end so you can draw it out, a technique that must be managed carefully to avoid sloshing the propellant around uncontrollably. You also have to solve the maddening problem of simply measuring how much propellant you have, because gauging the amount of a floating, sloshing, partly boiling liquid in a tank with no up or down is far harder than reading a fuel gauge on the ground. Every intuition you have about handling liquids, built over a lifetime under gravity, is wrong in orbit. And the engineers have to replace all of it with careful, deliberate techniques for herding weightless cryogenic fluid across the gap between two ships, a task with almost no real-world precedent at this scale. And wrapping around all of that is the physical act of the transfer itself, which requires bringing together two of the largest objects ever flown in orbit, and connecting them intimately enough to move propellant between them. Two starships, each one of the biggest spacecraft ever built, must find each other in orbit, approach, and dock, joining together precisely so that propellant lines can be mated and the transfer can begin. Docking two spacecraft is difficult even at small scale, and has historically been one of the more dangerous maneuvers in spaceflight, requiring exquisite precision to avoid a collision between vehicles moving at thousands of miles an hour. Doing it with two enormous ships, and then establishing not just a structural connection, but a sealed, leak-free, cryogenic propellant connection through which supercold liquid can be pumped in large volumes without freezing solid, without leaking, without letting air or contamination in, is a formidable engineering challenge on top of an already formidable one. The connection has to handle the extreme cold, the pressures, the flow rates, and it has to do it reliably, because a failure during propellant transfer, a leak of methane and oxygen between two joined ships, is exactly the kind of event that ends in an explosion. So the transfer is not only a fluid dynamics problem, and a thermal problem, and a weightlessness problem. It is also a docking problem, and a plumbing problem, and a safety problem, all at once, all of them having to be solved together in orbit far from any help, with an enormously expensive and eventually crude mission riding on getting every part of it right. And engineers are not helpless before all of this, because a whole arsenal of clever techniques is being developed to tame each piece of the problem, and understanding them shows that this is a solvable challenge, not a magical one. To fight boil-off, The tanks can be wrapped in advanced insulation and shielded from the sun. And the ships can be oriented so that they cast their own shadow over the propellant, keeping it in the cold and dark as much as possible. And the propellant itself can be loaded extra cold, subcooled below its normal temperature, giving it a buffer of margin before it begins to boil. In time, active cooling systems, essentially refrigerators for the tanks, could keep the propellant cold indefinitely, though that adds its own complexity. To solve the weightlessness problem, the settling thrusters gently push the liquid where it needs to go, and careful design of the tank internals and outlets helps gather and guide the floating fluid. To handle the rendezvous and docking of two giants, precise sensors, guidance, and automated control systems bring the ships together safely, building on decades of docking experience but scaling it up. And to manage the whole campaign, the sequence of launches and transfers is choreographed to minimize the time the propellant spends waiting and losing to boil off. None of these techniques is science fiction. They are engineering, hard engineering, being actively developed and tested. The point is not that the problem is unsolvable. It is almost certainly solvable, but that solving it requires getting a large number of these difficult techniques all working together, reliably, at full scale, in the unforgiving environment of orbit, which is a very different thing from solving any one of them on paper. The tools exist, or are being built. The challenge is making them all perform, together, on the day it counts. And if you are wondering whether anyone has ever transferred fluids between spacecraft before, the answer reveals exactly why this particular version is so uniquely hard. Fluids have been moved between spacecraft in orbit, but only in ways that dodge the hardest parts of Starship's problem. For decades, spacecraft have transferred certain propellants that are far easier to handle. Storable liquids that stay liquid at ordinary temperatures and do not boil away, pumped in modest quantities to keep space stations and satellites topped up. Robotic missions have practiced delicately refueling satellites with small amounts of fluid. So the general idea of moving liquid from one spacecraft to another is not brand new. But every one of those cases avoided the specific combination that makes Starship's tasks so brutal. They use small quantities, not the hundreds of tons Starship needs. They used room temperature, storable fluids, not cryogenic propellants that are hundreds of degrees below freezing and boiling away every minute. And they did it slowly, on their own schedule. Not as part of a frantic campaign racing against boil-off. Cryogenic propellant transfer, at large scale, at high speed, between huge vehicles, is a different beast entirely, and it has essentially never been done, which is precisely why it stands as the great remaining obstacle. The world has learned to pass a cup of easy liquid gently between two small partners. Starship has to pour an ocean of the coldest, most volatile liquid imaginable, quickly, between two giants before it all boils away. The precedents prove the idea is possible. They also make painfully clear how far beyond those precedents Starship has to go. So now you can see why this single problem stands where it does, blocking the path. Because absolutely everything downstream of it depends on it, and nothing can proceed until it is solved. Think about what refueling unlocks, and therefore what its absence blocks. Without orbital refueling, a reusable Starship can reach orbit and do useful things there, deploy satellites, carry cargo to low orbit, and those are real and valuable capabilities. But it cannot go to the moon. The entire plan for landing astronauts on the lunar surface, the mission that a great deal of national and commercial hope is riding on, depends on a Starship being refueled in orbit before it heads for the moon, because without that top-up, It simply does not have the propellant to get there and land. So no refueling means no lunar landing. Full stop. And beyond the moon, the dream of Mars is even more dependent on it, because a Mars mission requires vastly more propellant still, gathered in orbit before the long journey out. The whole vision of Starship as a reusable interplanetary transport, the thing it was fundamentally created to be, collapses without orbital refueling. Because that vision is built entirely on the idea of filling ships up in space and sending them onward. This is why it is fair to call it the single problem standing between Starship and its operational missions. It is not one obstacle among many equal ones. It is the keystone, the piece that holds up the entire arch, and until it is in place, the arch cannot bear any weight at all. The rocket can be perfect in every other respect, and it will still be stranded in low orbit, magnificent and grounded from its true purpose, until this one capability is proven. It is a strange and humbling situation to have built the most powerful flying machine in history and to have it held back not by any limit of its engines or its structure, but by the need to perform one specific task it has never yet done. All that power, all that engineering, all that ambition gathered into a vehicle that can shake the ground and touch the edge of space, and the whole of it waiting on the outcome of a single delicate experiment yet to be run. That is how much rides on this one problem, and why. Of all the challenges Starship has faced and will face, this is the one that truly deserves to be called the wall. And it is worth dwelling on what solving this actually unlocks, because the payoff is not just a moon landing, it is a fundamental change in the economics of leaving Earth. Today and throughout the entire history of spaceflight, the crushing constraint has been that everything a mission needs for its whole journey has to be launched, all at once, from the ground. Up out of Earth's deep gravity well, at enormous cost. Orbital refueling shatters that constraint. It means you can send a vehicle to orbit carrying almost nothing but itself and fill it up there, which means the same reusable ship can be topped off and sent anywhere, again and again, refueled between trips like a truck at a depot rather than thrown away like a bullet. It turns the rocket from a one-shot cannon into a reusable vehicle in a transportation network, and it makes the propellant, rather than the rocket, the main thing you are buying, which is transformative because propellant is cheap and rockets are not. A gas station in orbit, in other words, is the thing that could finally make spaceflight less like an Apollo-era stunt and more like an airline. The same vehicles flying over and over, refueled between missions, carrying ever cheaper payloads ever farther. That is the real prize hiding behind this one technical problem. It is not merely the key to the moon. It is the key to a completely different cost structure for everything humanity might ever want to do beyond Earth, which is exactly why so much rests on it, and why it is worth the years of struggle to get right. The single problem is a wall, yes, but on the other side of it is not just a destination. It is a doorway to a fundamentally cheaper way of moving through space, and that is what makes it worth all the difficulty. And there is a clock ticking on all of this, because Starship's refueling problem is entangled with a national timeline and a geopolitical race. The plan to return American astronauts to the surface of the moon depends directly on Starship being able to refuel in orbit, because the lunar lander for that mission is a version of Starship. And it cannot reach the moon without being fueled up in orbit first. That means the schedule for one of the most watched national space efforts in a generation is, in a very real sense, gated by this single technical problem, and any delay in cracking orbital refueling ripples straight into a delay in landing astronauts on the moon. And this is unfolding while another nation, moving with steady determination, pursues its own plan to put people on the lunar surface, turning the whole thing into a race with real stakes for national prestige and leadership. So the pressure on this problem is not just engineering pressure. It is the pressure of a deadline, of a rivalry, of a watching public and an anxious agency. All of it bearing down on the same delicate act of transferring cold liquid between two ships in orbit. The problem would be hard enough in a vacuum. It has to be solved on a clock, under scrutiny, with a great deal more than just a rocket program riding on the outcome, which raises the stakes on every test and every delay and turns a difficult piece of engineering into the pacing item for a nation's return to deep space. So where does the effort actually stand, honestly? Because it is important to be accurate about what has and has not been done. Real progress has been made, and it should not be understated. SpaceX has demonstrated the ability to move propellant between tanks within a single Starship in flight, a small-scale internal test that proves some of the basic principles. The company has developed the tanker and depot versions of the ship in its plans, and has been working steadily toward a full demonstration of transferring propellant from one Starship to another in orbit, the true test of the capability, which is a milestone still to be accomplished at the time this matters most. Starship itself, meanwhile, has continued to mature, moving through successive versions, achieving orbital flights, catching its booster, and beginning to deploy operational satellites, so the vehicle around the problem is advancing rapidly. But the specific, full-scale, ship-to-ship orbital propellant transfer, done reliably at the volumes and cadence a real mission remains the great unproven step. The demonstration that everyone in spaceflight is waiting to see, because until it is done, the operational deep space missions cannot be scheduled with confidence. So the honest picture is of a program that has conquered an astonishing list of hard problems and now stands before the hardest and most pivotal one, having laid the groundwork, built the tools, and proven the pieces, but not yet performed the full act on which everything else waits. The wall is still there, closer than ever, being steadily approached, but not yet climbed. And this points to a strange gap between how the public sees Starship and where the real difficulty lies, a gap worth naming. What the world watches and what makes the headlines are the spectacular, visible moments, the thunderous launches, the fireballs, the astonishing sight of a booster being caught out of the sky by mechanical arms. Those are the images that make people feel the program is nearly finished, that the hard part is behind it, that a rocket which can do all that must surely be ready to fly to the moon. But the truly decisive problem is almost invisible, because it happens quietly, in orbit, out of sight, and involves no fire or spectacle at all, just two ships joined in the dark, moving cold liquid between them. The most important thing standing in Starship's way is not one of the dramatic moments everyone watches. It is a subtle, undramatic act of fluid handling that would barely register on camera, and that is precisely why it is so underappreciated. People calibrate their sense of a rocket's readiness by the fireworks, and by that measure, Starship looks essentially done. But readiness for its real missions is calibrated by the quiet transfer, and by that measure, the hardest step is still ahead. This mismatch between the visible drama that suggests completion and the invisible problem that gates everything is why so many are surprised to learn that a rocket this capable still cannot go to the moon. The spectacle is solved. The plumbing is not. And it is the plumbing, not the spectacle, that holds the key. and the path to proving it will not be a single dramatic leap, but a careful ladder of demonstrations, each one testing a piece of the problem before the whole is attempted. The first rung, moving propellant between tanks inside a single ship, has already been climbed, proving that cryogenic liquid can be settled and moved in weightlessness at a basic level. The next great rung is the true ship-to-ship demonstration, launching 2 starships, bringing them together in orbit, connecting them, and transferring a meaningful quantity of propellant from one to the other, watching closely to see whether the settling works, whether the connection holds, whether the boil-off can be managed, whether the quantities can be measured. That single successful demonstration would be one of the most important milestones in modern spaceflight, the proof that the keystone can be set. From there, the challenge becomes scaling up, doing it with the full quantities a real mission needs, doing it repeatedly and quickly enough to fill a depot before boil-off wins, and finally doing it as part of a complete campaign that fuels a ship and sends it onward. Each of these steps is a chance for something unexpected to go wrong, some behavior of the fluid or the hardware that only reveals itself in the doing, because this is genuinely new territory, and the only way to truly learn it is to fly it. That is why the program advances, by testing, by flying and failing and flying again, gathering the hard data that no simulation can fully provide. The ladder is visible, the rungs are known, and the climb is underway, but the crucial rungs, the full-scale ship-to-ship transfers, are still above, waiting to be reached, and no one can be completely certain what surprises they hold until the ships are actually up there, joined, and pumping. And it is worth being fair and acknowledging that reasonable people could point to other candidates for the single hardest problem, because Starship faces several deep challenges, and they are connected. Someone might argue that the real gating problem is reusing the ship itself, surviving the fiery return through the atmosphere, and refurbishing the vehicle to fly again quickly. Because the heat shield that protects Starship on re-entry has been one of its most stubborn engineering challenges, and rapid reuse is essential to the whole economic case. Someone else might point to reliability, simply getting the vehicle to perform consistently, flight after flight, without failures, which any operational mission obviously requires. And these are real and serious challenges. But notice how they connect back to the same place. The reason rapid, reliable reuse matters so much is precisely that the refueling architecture demands a high flight rate, many tankers launched in quick succession, which is only possible if the ships can be reused rapidly and reliably. So the reuse problem and the reliability problem are, in large part, in service of the refueling problem. Prerequisites for it, rather than alternatives to it. Solve reuse and reliability perfectly, and you still cannot go to the moon without orbital refueling. But you cannot achieve practical orbital refueling without solving reuse and reliability first, because you need to fly all those tankers. Seen that way, refueling is not just one problem among several. It is the summit that the other challenges are the climb toward, the capstone that gives all the other hard-won capabilities their ultimate purpose, and the single thing that, once achieved, turns a very impressive orbital rocket into the interplanetary transport it was always meant to be. And there is a fragility to the whole scheme that is worth appreciating, because a refueling campaign is only as strong as its weakest link, and it has a great many links. Consider what a single mission actually asks. A series of tanker launches, each of which must succeed, each ship reaching orbit, finding its target, docking and transferring its load without failure. A depot that must hold its precious cargo cold and intact for the duration. A final ship that must arrive, connect, and take on its full load. And all of it racing against boil-off, so that a delay anywhere, a scrubbed launch, a failed docking, a leak, does not just lose one step, but threatens the whole accumulated effort. As the propellant already gathered continues to boil away while the problem is sorted out. A campaign like this has no room for the ordinary rate of failure that spaceflight has always lived with, because the failures compound and the clock never stops. This is why the demand is not merely to perform the transfer once, but to perform it, and everything around it, with a reliability and a speed that no rocket program has ever achieved, launch after launch, transfer after transfer, flawlessly enough that the campaign holds together before the fuel escapes. The single problem, in its fullest form, is not a single act at all. It is the demand for a whole system of difficult acts to work together, repeatedly and quickly, and almost perfectly, which is why, even as the pieces are proven one by one, the full capability remains the towering challenge that it is. Look up at the idea of it, a starship in orbit, gleaming, nearly empty, waiting, while another rises to meet it, and the two great ships join in the silence and the cold to pass propellant between them, and it is easy to see it as a small and technical thing, a detail, a plumbing job in space. But it is the hinge on which the whole future turns. Every ambition riding on Starship, the return of astronauts to the moon, the first human journeys to Mars, the entire vision of a reusable transport that opens the solar system, waits on this one act being mastered, this quiet transfer of cold liquid between two ships in the dark. The rocket is built. The power is real. The landings are proven. And still it waits, held back not by any lack of might, but by the delicate, unglamorous, fiendishly hard problem of moving fuel from one tank to another, where there is no up and no down, and the fuel itself is always trying to boil away and escape. That is the single problem standing between Starship and its first true operational mission, and when it is finally solved. On some day, when two ships meet in orbit, and the propellant flows cleanly from one to the other and holds, the wall that has stood in the way of humanity's return to deep space will quietly come down, and the largest rocket ever built will finally be free to do the thing it was always meant to do. Not just to reach space, but to leave. There is something fitting, almost poetic, about the fact that the last great obstacle is not a matter of power, but of finesse. Humanity has proven, over and over, that it can build machines of overwhelming force, that it can hurl enormous masses off the planet on pillars of fire. What it has not yet proven is that it can do the delicate thing, the patient thing, the transfer of a fragile, fleeing liquid from one ship to another in the cold and the weightlessness where none of our instincts apply. Brute force got us to orbit. Only finesse will get us beyond it, cheaply and repeatedly, and finesse is harder, because it cannot be muscled. It has to be understood and practiced and gotten exactly right. So the whole vast future that Starship represents, the moon, Mars, the opening of the solar system to reusable ships, waits now not on more thunder, but on the quiet mastery of a single subtle act. The rocket has done the roaring. What remains is the whisper of liquid crossing between two vessels in the dark, and when at last that whisper holds, everything else that has been dreamed becomes, for the first time, actually possible.